So we proved the theorem, which had a red star on it. It said if lambda 1 to lambda k are distinct real eigenvalues, then corresponding eigenvectors v1 to vk are linearly independent. What would be a reasonable and applicable corollary of this?
They form a basis for RK.
Okay, so suppose we're doing an n by n matrix. An n by n matrix with blank distinct eigenvalues. N is
Diagonalize.
well, except you're not saying it quite right.
Diagonalizability.
There you go. An n by n matrix with n distinct real eigenvalues. I keep putting the real in because we have mentioned complex and we're going to come back to that. N by n matrix with n distinct real eigenvalues is diagonalizable because you'll have corresponding eigenvectors, n of them, that will be linearly independent. And if you have n linearly independent vectors in Rn, they span and therefore form a basis, right? So you have a basis consisting of eigenvectors, which means you can use change of basis formula and diagonalize.
What happens if they're not real?
Then you would have to allow yourself complex eigenvalues and complex eigenvectors, and that's sort of not what you mean normally when we're talking about we're talking about diagonalizable with a basis for Rn. I'm not talking about stuff with complex entries at this point. That really belongs in a second course, but I'm going to do a little bit on that probably next week. All right, so the question is, what if you don't have n distinct eigenvalues? And we've already seen examples of this on Monday. We saw that you could have repeated eigenvalues and the stories could be different. So recall that we had examples that on Monday we had examples of matrices A and B with lambdas being 1, 1, and 2. One of those matrices there was a basis of eigenvectors, and the other matrix there was not. So one example was diagonalizable, and the other weren't. And I actually did mention vocabulary words then that distinguish the two things. Besides Cameron, does anybody remember what they were?
Geometric and algebraic multiplicity.
Yeah, geometric and algebraic multiplicity. So, definition, if lambda is an eigenvalue, let M be the multiplicity with which T minus lambda appears in the characteristic polynomial. So by the multiplicity, I mean the exponent that appears on t minus lambda to the n, i.e. p of t is t minus lambda to the mth times q of t, where what?
Q of t is divisible by t minus lambda.
Right, where there's lambda is not a root of q of t. So I've taken out the maximum power of t minus lambda I can. Right, so t minus lambda does not divide q of t, meaning lambda is not a root of q of t. Then m is called the algebraic multiplicity. Not surprising, right? Because we're talking about algebra here. On the other hand, we looked at what?
Geometry.
And that is what?
The actual number of distinct eigenvectors in the eigenspace.
No, you say that right. Distinct is not a good word.
Linearly independent?
Yes, that's a good word. The geometric multiplicity which we'll call d of lambda is equal to the dimension of the lambda eigenspace. So that's the number of linearly independent eigenvectors with eigenvalue. So Cameron already conjectured one thing which we're going to prove today.
E of lambda is
E of lambda is the eigenspace for eigenvalue lambda. So that's the dimension of the null space of A minus lambda I. So the conjecture which we're going to prove is, what do you know about
the geometric multiplicity?
the geometric multiplicity?
Less than or equal to the algebraic.
It's less than or equal to the algebraic. You can't have a larger dimensional eigenspace than you have the number of times it appears as a root. And also, what must be true by definition of eigenvector or eigenvalue? Greater than 0 or at least 1. Right? There must be at least a one-dimensional eigenspace, or else it's not an eigenvalue. Lambda is not an eigenvalue. So, give me what you think is true, and then we'll see if we can understand why, about the relationship between these notions and being able to diagonalize. What happened when we were able to diagonalize that did not happen when we were not able to
If it is
diagonalize?
diagonalizable, then the geometric multiplicity equals the algebraic multiplicity.
For
All eigenvalues.
all eigenvalues. And vice versa, conversely. So A, or the linear map, I don't know which notation we're using at this point, T or matrix A, whichever, is diagonalizable if and only if every geometric multiplicity is equal to the corresponding algebraic multiplicity for all eigenvalues lambda I. Okay, so it has to hold on every single one. Okay. So this gives you a criterion to check, and you've got web work to play with starting today that gives you numerical examples where you're supposed to compute these things and decide if you're diagonalizable or not. Okay. Oh, I had board left. Oh well.
Did we find diagonalizable?
We did. I'm pretty sure we did.
I mean, I know what it means. I don't.
Did we not really?
I don't think so.
Yeah, I don't think I had the formal proof, or not proof.
That's a definition. So, all right, so recall, even if I didn't say it, it's in the book, recall T, or matrix A, is diagonalizable if there's some basis. I certainly said this, maybe I didn't write it down. Some basis script B, so that
T and B is diagonal.
the matrix with respect to that basis is a diagonal matrix. This is how I motivated looking for eigenvalues and eigenvectors in the first place. But maybe I forgot to say this word. So I apologize if I did. So this is equivalent to saying that the linear map or the matrix is diagonalizable is equivalent to saying what?
That it's similar to some diagonal matrix.
It's similar to a diagonal matrix, but what has to be true about this basis? If you have a diagonal matrix, that means the vectors in the basis satisfy what?
They span around.
No, but specifically diagonal. What must be true about each of these basis vectors?
Orthogonal?
No.
Linearly independent.
That's always true for a basis. What specifically must be true?
Eigenvectors.
Thank you. There's a basis for Rn consisting of eigenvectors. We did say this. Maybe I didn't write it down officially. Somebody will have to check all the tapes.
Well, not anymore. Now that we have them.
So now this makes more sense then? Okay, well I'm glad I had the extra space in the book. It was there for a reason. Alright, so let's talk about these two propositions and then I want to do a couple of days of applications of this stuff. Alright, so why is D between 1 and m? So it's got to be at least 1, as I already said, by definition of eigenvalue. Say why.
Non-zero.
So if lambda is an eigenvalue, there is a non-zero vector that is an eigenvector. Therefore, you have at least a one-dimensional space of eigenvectors, because that non-zero vector spans a line. Okay, so the dimension of the eigenspace has to be at least 1. What isn't obvious, and when I first learned this stuff, it actually sort of surprised me, but in hindsight I think I was sort of silly, but what isn't obvious is that you can't have any more dimension of eigenspace than you have algebraic multiplicity.
All the multiplicities added together are going to be n. The number
True.
of multiplicities. And if one was greater than.
Well, I mean, so that's going to be part of our proof of this guy.
Okay.
But, you know, I actually sort of said this the other day, when we had 1, 1, and 2, and we only had one linearly independent eigenvector for eigenvalue 1, why couldn't there be some weird circumstance in which, even though the algebraic multiplicity for 2 was just 1, it only appeared once on our list, but why couldn't there perhaps be a plane's worth of eigenvectors?
Because that would give you a second eigen.
But,
The second.
well,
It
but
would take two things to span the plane.
I know. But if you don't know that the geometric multiplicity is in most the algebraic, why couldn't you somehow miraculously have more D than you have M? I mean, you can't. So it's hard to sit around trying to make an example where you can, because you can't. But it's not totally obvious. So why must d be less than or equal to m. So here's what I suggest you do. Let's use these d linearly dependent eigenvectors to build a basis. So let v sub 1 to v sub d be a basis for e of lambda. Now, this is a fact that I think you used in homework last semester, although you may not have had the homework problem to prove it. But I told you to use it anyway. Anytime you have a basis for a subspace of the space you're in, what can you always do?
Add more vectors to make it be a basis for.
Yeah. Augment that basis with n minus d more vectors so that you end up with a basis for Rn. So we can extend these d vectors to a list where we add on n minus d further vectors and end up with a basis for Rn. So the key thing here is that I'm using the ones I started with and making more. Do you guys remember what homework you did where you used this several times?
It was,
Yes.
That's probably asking too much.
it's stuff about like proving if something's
At m
a
plus b.
subset and it has the same dimension.
That might have come in there.
Maybe we're trying to add bases together.
There you go.
Oh,
When you wanted to prove the dimension of the span or the sum of two subspaces was the dimension of one plus the dimension of the other minus the dimension of the intersection. You used this idea several times. Good, Reese. So, what does the matrix for our linear map, let's call this basis script B. What does our linear map look like in this basis?
Well, V1 through VD all have
So, what does that tell me about my matrix?
it's on the diagonal, or the first D diagonals are all lambdas.
Okay. So this is a little d by d lambda times identity matrix. This is d, and this is d. What's down here?
Zeros.
Yeah, so that's what's crucial. The fact that these are eigenvectors means that each of them gets sent to lambda times itself plus nothing else. Now, what do we know about this part of the matrix?
I know the top D part is 0.
Do you?
No, I don't.
Don't say you do.
I thought I did.
Now, you don't know anything about what t of these is, do you? You have no information, we just picked them at random. So all you have is junk. You don't know what it is. But this is good enough. What are we trying to do? I've lost track. What are we trying to do?
D's.
And what is m?
Is the algebraic multiplicity.
M is the algebraic multiplicity. So what ought we to do if we're interested in
Take the determinant of this.
close? What do I want? Let's call this matrix regular B, just in case I started with a regular A, if the standard matrix for my linear map was A. What should I do with this matrix B? I should ask, what's the characteristic polynomial of my linear map? And remember, we argued that that characteristic polynomial is the same no matter what basis you use to represent the matrix. Determinant of A minus lambda I, or A minus Ti, is the same as determinant of P inverse AP minus Ti. So if you do any change of basis, so I said this, but I didn't write it out officially, so I'm writing it out now. Why is this true?
Because determinant, it goes by, it goes over multiplication.
Can you make that a more precise statement?
Because the determinant of P inverse will equal the determinant of, it will equal 1 over the determinant of P.
Okay,
And
so
that'll
what should
cancel
I
the
do
one.
with
You
this?
can distribute.
We can't distribute over a minus sign.
Yeah, you can.
Can you?
So I can write this as the determinant of P inverse A minus Ti and then P. Because a scalar multiple of the identity, if I put a P inverse on the left and a P on the right, identity commutes with everybody. So the P inverse and the P cancel out, so I get back to this. Everybody buy that? But then determinant of P inverse matrix P is the same as determinant without the P's and the P inverses because those cancel out. So pray compute the characteristic polynomial of this matrix. What is characteristic polynomial of this matrix B?
It would be t minus lambda 1 through I, wouldn't it? I mean, they're multiplying those together, t minus lambdas.
What about all this junk?
Worry about that.
Where we won't go back to something zero.
So I'm taking determinant of B minus Ti. So I'm going to take determinant, I'm going to subtract T from the diagonals. So that part I understand. But then I'm going to have junk here with junk minus T, junk minus T, junk, junk, junk.
We did some homework problem about determinants of block matrices.
We did in fact,
I don't think very hard with that.
And it had a 0 in the lower left. So
when you had a matrix that was of the form A0 CD, what was the determinant of that?
It completely ignored C, right?
It completely ignored C. It's the determinant of the two diagonal block pieces. Because of the zeros here, you guys
Yeah, it
did a proof of this.
clears out.
This is irrelevant
Or
or irrelevant. So what's this determinant equal to?
So
the determinant,
lambda minus T to
the
the D.
determinant of A minus,
So there's this stuff here.
because that's A.
This has 0. And then it has this stuff here.
So you have
The
the
minus T to
D
the and OD.
Yeah.
The minus T to the D.
times determinant of junk.
Determinant of this stuff, whatever. So that's going to be some polynomial. Agreed? I don't know what polynomial it is, but when this doesn't matter. And I'll get the determinant of this block. It's some polynomial in T of degree equal to n minus D. All right, why are we done? This is supposed to be the same as the original characteristic polynomial, in which we said the algebraic multiplicity was m. So could this exponent be any bigger than m?
No. If it was, then yeah.
Wait,
Is Q a claim to 0?
We don't know. Maybe it is. Lambda could be a root of this. But for sure, can this exponent be bigger than m? Look at the definition. This is supposed to equal t minus lambda to the mth times, I shouldn't have used q here, so let me call this something else. Let me call this k of t. And here we knew that q of lambda wasn't 0.
So m has to be greater than d.
M has to be at least d, right? You can't have a power here that's bigger than the power that appears here. That's the maximum power that's appearing.
Because then you can multiply k of t by lambda minus t to get g of t. If
No.
d was one.
No, this is the m is the largest power of t minus lambda that appears. So you cannot have a larger one appearing here. There is officially, we're using the fact that polynomials have unique factorization properties if you want to talk about that. I can to make a big deal about it. So this implies d less than or equal to m. And in fact, if it's less, to follow up on Ken's point, if d is less than m, then lambda will have to be a root of that part. Okay. All right, so what about the second proposition? So Cameron made a point earlier that he's forgotten.
Well, that sum of D has to be.
The sum of whom has to be what?
M has to be M.
The sum of the m's, so let lambda 1 to lambda s be the distinct eigenvalues. So I have s distinct eigenvalues. Each one of those has a d and an m. What do we know about the sum of the algebraic multiplicities? They add up to the degree of the polynomial, which is n. Right? Because these are all the roots of the polynomial. The polynomial has degree n. All right. Now what do we know about each d? We just proved it.
The sum is less than this. Less than or equal to N.
Each d is at most its corresponding m. So if I add up all the d's, the sum of all the d's is at most n. Alright, well, what do, if, if t is diagonalizable, what did we just say? We said that means there's a basis consisting of eigenvectors. So this number has to be what?
N.
Has to be n, because you can make a basis by picking di from each eigenspace. So if this sum is actually equal to this, what must be true here? Must be equal, right? Each di must equal the corresponding mi.
Why
If
is
you-
that?
Because if this number were less than this, we couldn't get n. So this number has to equal n, which means at each time you have to have equality. If some di were less, you could never catch them because of the inequality.
Why are those only one direction? Is that an if and only if statement?
Well, okay, now I'm going to I have to argue the other way. So if,
So the part about where if t is diagonalizable, then the sum of the di's is n, why is that the case again?
because you have a basis consisting of eigenvectors. So how are you going to pick up that basis? You're going to have to pick
Yeah.
this many
Okay.
from each eigenspace to get the basis. All right, now Jonathan's saying, in fact, we can turn this around. If each di equals mi, then we have equality here, which means that we have enough eigenvectors in each eigenspace to get a basis. So if this is true, then this is true, which implies it's diagonalizable. So in fact, you're right. It is. All right, so I want to do a couple of these. Actually, yeah, I want to do a bunch of applications. And if you like, this is why you might actually care about diagonalizing matrices, because it makes your life very easy for doing various sorts of applications. So why is diagonalizability useful. So we're going to do two major applications right now. Not both right this second, but one is if you have an n by n matrix A, you might want to compute the various powers of that matrix. And I'll show you why you might actually care about that. But even for 2 by 2s, if I just give you a random 2 by 2 matrix, you start squaring it and cubing it,
It's nasty.
it's going to get very nasty. But look, if A were a diagonal matrix, even my pet baboon can do this. How do you take the powers of this matrix?
Just
Just take the powers of the diagonal. That's it. So that's really nice. So, okay, so suppose you could diagonalize A and turn it into lambda. How would that tell you back what the powers of A are?
Well, then A would equal what P inverse lambda P.
No, the other way around.
Okay.
If you can diagonalize A, then there's a change of basis matrix that makes it become diagonal. So A is P lambda P inverse. And you're going to have to keep this straight, because for the applications we're going to do, you're going to have to get this right. Okay? So P here is the matrix whose columns are the what? The eigenvectors. These columns are the eigenvectors in the correct order corresponding to the eigenvalues you have down the diagonal of lambda. So if I take A squared, so I think you guys realized this back when you had some web work on this last semester.
Why is it important that these columns are eigenvectors in this application?
Because that's how you're going to find the P.
Oh, okay.
So what happens if you square A?
It just becomes P lambda squared.
Right. These guys cancel out in the middle.
Yeah, give me
So you have P lambda squared, P inverse. And so by induction, for those of you who wish to be pedantic,
AK equals P cap lambda K inverse. Okay.
so those of you who want to practice your induction proofs may so practice. Alright, so one of the main applications we're going to do of this is, well, there's actually two. One is called Markov processes, which show up a lot in statistics and other applications. Another is something called difference equations, which is a discrete math version of differential equations. And we're going to get to differential equations on Friday. So the two main applications I want to talk about are Markov processes, which ties in with probability and statistics, and the second is difference equations. So for example, I'm going to do a Markov process in a moment, but if you've never heard of a difference equation, well, the example we're going to do in a moment is what is the kth Fibonacci number? So that's really a linear algebra problem. Have you guys heard of the, everyone's heard of the Fibonacci sequence? Haley? Yes? No? So the Fibonacci sequence supposedly was discovered by Leonardo da Pisa, trying to do
Breed rabbits.
rabbit populations. So you start off with one rabbit and another rabbit, and then a minute later you have two rabbits. Wait a minute, that doesn't seem right. Then you have 1 plus 2, and you have 3. 2 plus 3 is 5. 3 plus 5 is 8. lot of you guys have seen this stuff. What do you know about it?
It like forms a spiral.
It's like,
Where you
There's a
can
way of
make a
visualizing.
it's like that little triangle.
Every fifth number is a multiple of
That's interesting.
That is interesting.
Is that
It's
true?
true. 5. And there's a discrete formula for them all.
All right, so what you're supposed to know something about is the ratios of these things. Do you not know that?
The golden
They go to the golden ratio. But what very few of you know probably is that you can give an explicit formula for what the kth number is.
To the end. You have to power to the end.
Okay, so where did that formula come from? So we're
numbers.
So we're all right. So we're going to show you where that formula comes from. The Markov process. I want to do an example for you. I'm making up numbers here. They have no bearing in reality. But suppose that there's a hypothetical colleague of mine with whom I play tennis regularly, and we've observed a certain pattern in the win-loss probabilities, depending on whether I've just won a game or just lost a game. So,
Is that kicking your bet on the tennis court again?
hmm?
Is that kicking your bet on the tennis court again?
That's it. So suppose that
Even the days off.
Fred and Ricky play tennis regularly, and it's discovered that if Fred wins a game, he is, let's say, 60% likely to win the next. And obviously 40% likely to lose the next. In tennis, there are no ties. On the other hand, if Ricky wins a game, he is 80% likely to win the next one.
Ricky is?
Yeah. I mean, for those of you who don't know to whom I'm referring, this goes back quite a ways.
I love Lucy.
And one of them smoked a lot and the other was a little overweight, so I'm not sure how accurate these numbers are. So the question I'm going to ask you is, they start playing. 20 years later, what is the win-loss ratio for each of them? So the question we're going to ask here is, so Markov processes in general model things where the probabilities don't remember histories. There's another situation where you might have this is you have U-Hauls distributed among 5 different cities. And because of the prevailing traffic of people wanting to go from city A to city B, if you're in one of the 5 cities, there's a certain probability that if the U-Haul's in a certain city like Poughkeepsie, there's a certain probability it will get driven to Boston, or to Laredo, or to San Francisco, or to Chicago, or to Minneapolis. And you have these numbers. And the question is going to be, given this 5 by 5 matrix of numbers, can you tell me down the road what the distribution of U-Hauls is going to be among those 5 different cities? This is what the linear algebra is going to tell you how to do. So the question is going to be, what is the steady state win-loss ratio? So what is perhaps not obvious to you guys, but we're going to prove it, is that in a situation like this where you're working with probabilities that add up to 1, there's always going to be a limiting distribution of win-loss ratios. No matter what you start with, it's always going to end up, as time passes, that you approach in the limit a certain fixed win-loss ratio or a certain fixed distribution of U-Hauls. So let's figure this out.
Adding up to 1.
Yeah, so probabilities add up to 1. So I'm going to build, so if Fred is 60% likely to win the next, he's 40% likely to lose. We don't have draws. if Ricky wins, he's 80% likely to win and 20% likely to lose. So, the question is going to be, what is called the transition matrix that gets us from state where we've gone from playing k games to playing k+1 games. So here's what we're going to say. So let's let x sub k, I'm going to make a sequence here, be the probability, let's say, that let's see what order I want to do here. So this is going to be the vector of probabilities. Is the probability that who's first Fred wins the kth game, and qk is the probability that Fred loses the kth game, which means what? If Fred lost, that means Ricky won. It doesn't matter how you say it, but we can be more PC and talk about, since it's always good for everybody to be a winner, let's do it to win. All right, so basic fact about probability here. This is about the limit of the knowledge I have for probability. But how do I compute?
Are you teaching it next semester?
I haven't learned it yet. What's the probability, given that Fred's won a certain game, we know that he's 60% likely to win the next one and 40% likely to lose it. So what's the probability that Fred wins the next game, the k plus first game?
Wait, sorry. Question. Just to visualize, it's a 50 shot of that first game.
So,
That's it.
so Gabe's asking a good question, which is, where do we start? I was going to get to that, so let me keep going and I'll get back to that. What's the probability that Fred wins the next game?
Well, it's the odds that he wins the first game.
No, it has nothing to do with the first game. The K, you mean the kth?
Yeah, it has to do
So
with
either he won the kth game or he lost.
Yeah.
Was 0.2
Yeah.
QK.
So if he won
Yes.
the previous game, there's a 0.6 chance that he wins the next one. So the probability that he won the kth game times the probability that if he won, he proceeds to win the next one. This is, what's this called, Bayes' rule or something?
Wait.
We're going to multiply the probability that we won the kth game times the data we're given here, namely, if I win, there's 60% chance I can go on and win again. But he could have lost,
0.2.
which is QK. So if Fred lost, there's only a 20% chance that he's going to win again.
And it says since the game's already happened, PK and QK are either 0 or 1, right?
No.
It's a pop-up.
No.
Yeah.
QK plus 1 is the complement of this. Right? What's the chance that Ricky wins the kth game? Well, if he lost the kth game, sorry, the k plus first game, right? If he lost the kth, there's a 40% chance that he's still going to win. And there's an 80% chance that if he won, that he'll win the next one. So I have what's called a transition matrix here. Namely, I can now look at this vector of probabilities, and I can say to transition from the vector in time k to the vector in time k plus 1 is given by this matrix that we just wrote down here, not in matrix form. It looks like that. And this is called the transition matrix.
Did you talk about a transition matrix last semester at all?
No. Oh, maybe. Did I?
Actually, the name sounds really familiar.
You might have seen the graph theory.
Probably not.
Remember having a web work that had to do with this?
Really?
It had to do with limits of,
We did stuff with fixed points where you iterated a function.
yeah.
Okay, well, okay, we are sort of headed there, but it wasn't, okay. So Gabe asked, what is the original starting probability vector?
I don't think it matters.
Oh, could this have been a difference of equations?
So there is some starting vector here at when we start with the 0th game. Well, there wasn't any probability, right? I mean, so there's some, but you can just say let x naught be some vector that tells us the probability leading into playing the first game. You can put a 1, 0, you can put a 0, 1, you can put a 50, 50. It's not going to matter, but it's an initial condition, if you like. Then what you see from that, though, is that x of 1 will be a times that initial 1. X of 2 will be a times x of 1, which will be a squared times the initial 1. And so as you go on, the kth vector is going to be given by the kth power of a times the initial vector.
So it's supposed to just, is it obvious that the initial
No,
thing? Okay.
it's not obvious. We'll see. No, so in real life you can say, well, let's suppose Fred starts with a 100% chance of winning the first game. So but all right, I'm not going to get there today. I'll have to finish this on Friday. But you already now see that I want to compute the kth power of a. So how am I going to compute the kth power of a? Obviously, I'm going to try to diagonalize a. So let's get that far today, and then we'll pick up with this on Friday. What are the eigenvalues of a? Trace is 1.4. Determinant 0.48 minus 0.08. What are the two lambdas? Their product is 0.4 and their sum is 1.4.
1, -1, -0.4.
1
Well,
and 0.4. This 1 is fascinating.
Isn't it negative 1 and,
No.
oh yeah, because they're the roots.
The roots. What do you notice about the columns of this matrix? They add up to 1. Why do they add up to 1? Because the probabilities have to add up to 1. That means 1 has to be an eigenvalue. So here's an exercise for you to ponder for Friday, and then we'll finish this up. If the columns of a matrix all add up to C, then C is an eigenvalue. So I mean take each column, add it up. Take each column, add it up. If those numbers are the same, that number is an eigenvalue. And what I will comment is, we'll see on Friday, you've got the 1, that's going to tell you have a steady state. And the fact that this number is less than 1 is going to say that it's going to disappear. Okay, so that's what we'll pick up with on Friday. Then we'll do Fibonacci, and then we'll start talking about differential equations.